Let us define what a coherent state is, uh, first of all, before moving forward. Coherent states are very important type of states in continuous variable quantum computing because through these particular type of states we can understand a lot about the dynamics which is going on when we do continuous variable quantum computation. So before we delve into this, let me define what is called as a displacement operator. So this is the first definition, and that definition is of what is called as a displacement operator. The displacement operator is defined as d cap alpha is equal to e raised to alpha a dagger minus alpha star a. So these are the creation and annihilation operators which we saw in previous videos. And this is how the displacement operator is defined, where alpha is a complex number. Now, there is some very interesting breakup or definition or derivation in uh, quantum mechanics, which is called as the Baker-Campbell-Hausdorff Baker-Campbell-Hausdorff formula. So it says that if we have this kind of a setup, if we do this kind of a transformation on an operator b cap, then I can decompose it and write it as b plus lambda times commutator of b and a plus lambda squared by 2 factorial times commutator of b. Now this is a very important decomposition, just like Taylor series, I would say, which is useful in deriving a lot of stuff. So that is why I'm mentioning it here, and I'll be using this extensively throughout this particular video. The other thing that I want to point out is that if we have something like this, e raised to a cap and e raised to b cap, note that these are operators and not numbers or scalar functions, then this is equal to a cap plus b cap. However, we will also have a commutator here. So you note that unlike with the scalar functions or numbers, we have this extra term when we deal with operators. So these two are important formulae that I will be using extensively. So keep in mind. So using this formula, the second one, I can also write the displacement operator as e raised to alpha a dagger, e raised to minus alpha star a, e raised to minus mod of alpha square by 2 a dagger comma a. Now we note that this is equal to minus 1. So this becomes equal to e raised to, let me just recollect. Um, okay, let's write it down. If there is a mistake, we'll clarify it. So this is e raised to mod of alpha square, e raised to alpha a dagger, e raised to minus alpha star a. So this is how we can decompose a displacement operator. So now that we learned a few things about the displacement operator, we will define what is called as a coherent state using this. So a coherent state is derived by applying this displacement operator on a single mode vacuum state. So if I apply the displacement operator on a single mode vacuum state 0, I get what is called as alpha, and this is called as a coherent state. This is the definition of a coherent state. It is a definition of coherent state. So a coherent state is a state which is derived by applying a displacement operator on a single mode or multi-mode vacuum state. So this is how a coherent state is defined. So now let us start with the first property of displacement operators and coherent states. So the first very important property of displacement operator and coherent states is, let us write the coherent state in terms of the number Fock state, single mode Fock states. So as we saw, as we had defined, alpha is equal to d cap alpha acting on 0. This is the definition of the coherent state, and this is what we had derived regarding the displacement operator when we decomposed it using the definitions above, where these are the creation and annihilation operators. Now, when this thing acts on the vacuum state, single mode vacuum state, I can derive it easily that this alpha is equal to e raised to minus mod of alpha square by 2 summation n equal to 0 to infinity alpha raised to n divided by root of n factorial into n. Now, how did I derive this? I derived this by opening this particular e raised to lambda a cap as identity operator plus lambda a cap operator plus lambda square by 2 factorial a cap square and so on. So this, if capital A cap, I replace it by small a cap and lambda as minus alpha star, and then I act it on this state, and then I similarly do it with this particular operator, then I will get this as the output, where there will be this factor e raised to minus mod of alpha square extra over there. So I can write this as the first property of the coherent states, that alpha is equal to minus mod of alpha square divided by 2 summation n equal to 0 to infinity alpha raised to n divided by root of n factorial into n. You can derive this easily, and I'm not uh, putting much time in deriving this because it can be done easily. The second thing is that let's write this coherent state in matrix representation. So if I write this coherent state in the matrix representation, then if we recall that n, let's say this particular state is there, single mode Fock state, it is given as this particular matrix 1 cross infinity. This goes up to infinity. There is a cutoff dimension, and I can write it as 1 cross n and cut it off at some particular point. But anyway, this is how we could write the single mode Fock states. And we just saw that the coherent state is a superposition of all the single mode Fock states. So I can write this as alpha is equal to, let me just write it down, e raised to minus mod of alpha square by 2. Let's take it out common. Let's first put n equal to 0. So this is like alpha raised to 0 by root of 0 factorial into 0 plus alpha raised to 1 by root of 1 factorial into 1 plus so on, alpha raised to infinity by root of infinity factorial by Yeah, but we always have a cutoff dimension. I'm repeating it again and again. So this can be written as alpha raised to 0 by root of 0 factorial, alpha raised to 1 by root of 1 factorial, and so on. So I can write the coherent state in a matrix form like this. Of coherent states is that they are not orthogonal. This is a very interesting property because usually when we talk about states, we find them always to be orthogonal, but coherent states are not orthogonal to each other. So if I have one coherent state and another coherent state and I take an inner product of it, this is what the inner product of these coherent states will look like. Let me prove this now. So if I write this alpha beta in a decomposed form, it can be written as n1 summation n1 equal to 0 to infinity alpha raised to n1. There will be a star here because we are talking about the dual. So this is n1 factorial, and there will be e raised to minus mod of alpha square by 2, and then we will write the decomposed form of beta, that will be equal to n2 equal to 0 to infinity e raised to minus mod of beta square by 2 beta raised to n2 divided by root of n2 factorial into n2. So let us take out the scalars which are not dependent on n. So this will become e raised to minus mod of alpha square plus mod of beta square by 2 summation n1 comma n2 equal to 0 to infinity alpha star raised to n1 divided by root of n1 factorial beta raised to n2 divided by root of n2 factorial n1 inner product n2. Now the Fock states are orthogonal to each other, so I can write this as n1 n2. They are orthonormal to each other, delta n1 n2. So if I use the property of delta, this becomes divided by 2 summation n equal to 0 to infinity alpha star raised to n divided by n factorial. This is beta raised to n. So I write this as n1 is equal to n2 is equal to n, and from there using the Kronecker delta property, and I can write it in this form. So you see that this is equivalent to e raised to alpha star beta divided, not divided, yeah, this is what it is equal to, this thing. So we get that when we take an inner product of coherent states, it is equal to mod of alpha square plus mod of beta square by 2 e raised to alpha star beta. And if I take a mod of this, which is the probability of finding beta, pro- uh, provided that we are doing a measurement with in the alpha basis, then this is equal to e raised to minus mod of alpha minus beta square. You can just take a mod square of this and it will turn out to be this. So these two are important formulae for coherent state. inner products. Property, or let us start with the displacement operators. So I claim that d dagger of alpha is equal to d of minus alpha. This is just easy to prove because we know that d of alpha is equal to e raised to alpha a dagger minus alpha star a. D dagger of this, if I take a dagger of this is equal to, the right side hand side is equal to e raised to alpha star a minus alpha a dagger. But then this is equal to e raised to minus of alpha, or let me write it in this way, minus of alpha a dagger minus of minus alpha star a. So this is equal to, I as I claimed, d of minus alpha. Next, I claim that inverse of this operator is equal to this. That means that the displacement operator is unitary. So it is easy to prove. In fact, we need to prove that d dagger of alpha into d of, or d of alpha into d dagger of alpha. Let me just uh, write it in this way. So see, d inverse alpha is equal to d dagger alpha. This is what we want to prove. In other way, we want to prove that d of alpha, d dagger of alpha is equal to identity operator. I just multiplied by d of alpha on the left hand side, and d of alpha into d inverse alpha should be equal to identity. So this is what it is. And the right hand side, d of d dagger alpha is here in the left hand side. So this is another thing that, another way of saying the same thing, and we want to prove this. So I can just replace d of alpha here. So d of alpha is equal to what? Alpha a dagger minus alpha star a, and d of this thing, I let me write it as d of minus alpha. So as I just proved in the previous one, so this is d of minus alpha a dagger minus alpha star a. Now I can use the Baker Campbell Hausdorff formula and write this as alpha a dagger minus alpha star a plus minus of alpha a dagger minus alpha star a. So you see that this and this will cancel, this and this will cancel, and then there will be a commutator. So alpha a dagger minus alpha star a, comma, minus alpha a dagger minus alpha star a. This commutator, this divided by 2. You can easily prove that this is equal to 0. I'm not going to do that. You just use the commutator properties, that a comma a dagger is equal to 1 and so on, and you will see that it's just some algebraic manipulation that you need to do. And here this, because of alpha and minus alpha and all, these things get cancelled, and you will see that this is like e raised to 0 into e raised to 0, which is equal to nothing but the identity operation. So we see that the displacement operator is unitary. Now let us go on to the sixth property, which is also one important property, that if I transform this matrix, uh, if I transform the operator, annihilation operator a cap, using the displacement operators, then this is equal to a cap plus alpha times the identity. So let me just prove it again using the Baker Campbell Hausdorff formula. So the Baker-Campbell-Hausdorff formula, we, if you recall, was e raised to minus lambda a b e raised to lambda a. It is equal to b plus lambda b comma a plus lambda square by 2 factorial b comma b comma a plus so on. So I use that in place here because d dagger alpha is equal to d raised to e raised to minus uh, it is equal to d of minus alpha from the previous properties. So this I can write it as e raised to minus alpha minus of, yeah, minus alpha a dagger, or let's take this minus inside, minus of alpha star a e raised to alpha a dagger minus of alpha star a. So as I said, using this particular formula, this can be written as equal to a cap plus a cap comma alpha a dagger minus alpha star a plus a cap comma this commutator inside divided by 2 factorial and so on. So now this commutator a cap alpha a dagger minus alpha star a is equal to nothing but just alpha. So I can write this commutator as, let me just break it down, a cap alpha times a cap a dagger minus alpha star times a cap comma a cap. This is equal to 0 and this is equal to 1, so it's just alpha. So you can see that this is equal to a cap plus alpha times identity. So we just proved that this is true. Now let's move on to the next property, that d dagger alpha a dagger d alpha is equal to a dagger plus alpha star times identity. I won't prove this. The proof is exactly similar to the previous one. We just replaced a with a dagger here. That's it. And you can see the consequences here on the right hand side. Now let's operate this on the number operator. Similarly, let's check what happens if we transform the number operator using the displacement operators. So if I do that, it is equal to a dagger a plus alpha a dagger plus alpha star a plus mod of alpha square. This is what you will get. So you just basically, again, you have to use the Baker-Campbell-Hausdorff formula, or you can use this particular property. Let me just prove it without the Baker-Campbell-Hausdorff. So this is equal to d dagger alpha a dagger a d of alpha, which is equal to d dagger a dagger d of alpha d of alpha this dagger a d of alpha. And what I just did is I used this property that d of alpha d of d dagger alpha is equal to identity, because we had proven that this is equal to d inverse alpha. So d of alpha into d inverse alpha should be identity. So I just put this in between here and I expanded this particular formula. Now this thing we already saw is equal to a dagger plus alpha star times identity, and this is equal to alpha, oh sorry, a plus alpha times identity. So that is what we proved, a dagger plus alpha times plus a plus alpha. So this is how the number operator gets transformed by using the displacement operator. Now let's move on to the other property. What happens if I act them on the quadrature operators? So this is what I claim, that d dagger alpha x cap d of alpha is equal to x plus root of 2 times h bar real part of alpha times identity. So the proof is easy. We just need to substitute x cap is equal to a cap plus a cap dagger by root 2. And I think let's forget this h bar here. Okay. And doing that, you will be able to prove that relation something like this, similar to this, by just using this particular formula of the quadrature operators and then using these relations 6 and 7. Use relations 6 and 7 to prove 9. Then let's look at another property, or let me just prove it for simplicity, then the next ones I will not prove. So this is equal to a cap plus a cap dagger by root 2 into d of alpha, which is equal to d dagger alpha a d, let me just not write this, by root 2 plus d dagger a dagger d by root 2, which is equal to, what was this, a plus alpha by root 2 plus a dagger plus alpha star by root 2. So this we club together, plus alpha star by root 2. This is equal to x cap plus alpha star is what? Real part of alpha by root 2. So I multiply by root 2 here and divide by root 2 here. So this should be giving me real part of alpha. So we just saw that d dagger of x cap d is this, as I had just mentioned over here. Now let's move on to the next property. D dagger alpha acting on p cap d of alpha is equal to p cap plus root of 2 imaginary part of alpha times identity operator. Again, just use the definitions and you will get this. So 6 and 7, and use the method of the previous one and you will get this relation. Then I define two more operators, which are special cases of different displacement operators. X cap of x, I define this as d cap of x by root 2 and z cap of p, and this is again a definition and I call it as by root 2. So this is called as a pure displacement operator, pure x displacement operator. And this is called as a pure p displacement operator. Now the thing is that why we call this as a displacement operator, I'll just come to it when I will talk about Wigner functions and the optical phase space. For now, let's just say that this is the optical phase space and of the states, and these are average x and average p of the quantum states. So what this pure x displacement operator will do is that displace the state along the x-axis, and pure p displacement operator will displace the state purely just around the, and this is also the reason why this particular uh, operator is called the displacement operator is because that it displaces a state from one position to another position. I'll come to it, don't worry about it. When I'll talk more about the phase space in continuous variable quantum computing. And this was, sorry, this was property 11. Then let's go on to property 12. Okay, the property 12 is x cap of x can be written as exponential minus x cap p cap by h bar. H bar you can ignore, let's write it that way. And z of p cap is equal to, or z of p is equal to exponential, or sorry, this is not x cap, this is just x scalar ip by h bar. This is how I define x and p. So I can just write them in this form. I'll not, okay, I'll prove it. So this is the proof. So we have x cap acting on x is equal to d cap of alpha is equal to x by root 2 is equal to e raised to alpha a dagger minus alpha star a, which is equal to e raised to x a dagger minus x a by root 2, which is equal to, I just substituted alphas here, e raised to x by root 2 a dagger minus a, but p cap is equal to minus I a minus a dagger by root 2. So this implies that a dagger minus a is equal to I root 2 times p. So I just substitute it and I get this x cap of x in the exponential form as this. I'm ignoring h bar here. So I can just ignore h bar. So this is what it is. Yeah. And you can do that similarly for p cap of p. Now let's move on to the next property 13. The next property is x dagger of x, x cap x of x. This is what we had defined now earlier. These operators, pure x displacement operator. So this displaces by this much amount along the x-axis. This is what I had just mentioned. And z dagger p, p cap, zp is equal to p cap plus p times identity. Now to prove this, just use this particular properties and you will be able to prove it. The properties that I'm asking you is to use is 9 and 9 and 11, 9 and 11 for this first one, and 10 and 11 for the second one. So you use these to prove this and this one. I will not write the proof. It is particularly straightforward. Now let us move on to the 14th property. 14th property says that coherent states are eigenvectors of the annihilation operator. This is also used as another definition of coherent states, that they are eigenvectors of annihilation operators. So let us prove this very important property of coherent states. So let us just write the right hand side in a more decomposed form, is equal to alpha times d cap of alpha times the single mode vacuum state. This is what the definition of alpha was, that as we defined earlier. And now I will use some properties that we defined earlier. So we had proven that d of alpha, d dagger alpha, sorry, d dagger of alpha, a d of alpha is equal to a plus alpha times identity. So what we can do here is, let us do some manipulation and okay, let us write the left hand side here. So this left hand side is equal to d of alpha acting on 0. I use the definition of alpha here. Let's just forget the right hand side. I'll write it down. A cap acting on d of alpha 0. But you know that a cap acting on d of alpha is equal to, I take this over here. So a cap acting on d of alpha is equal to d of alpha a cap plus plus alpha times d of alpha. Now you'll be wondering how I got it. I got it by multiplying d of alpha from left hand side. So on the left hand side, d of alpha into d dagger alpha is equal to identity because of the unitarity property. And here this thing remains d of alpha. So that is how I got this particular relation. So this thing here I can substitute with this one's right hand side. So this becomes d cap of alpha a cap plus alpha times d cap of alpha times acting on the single mode vacuum state. So this when acts on the single mode vacuum state, it should give me, so because this a cap acting on 0 is 0 times 0, this is how the definition of annihilation operator is. This state is, we can, the first term we can consider to be 0, and the second term becomes d cap of alpha 0. But then the definition of d cap of alpha acting on single mode vacuum state is equal to alpha, get alpha. So we saw that a cap acting on alpha is equal to alpha times alpha. So we just proved that alpha is an eigen state of a cap. Now what we will do is, in the next video we will learn about a few properties about the phase space and Wigner functions, and understand these, why we call this particular state as a displacement operator, where does a coherent state lie, how to visualize it on an optical phase space, a quantum optical phase space, and how do we understand a few operations here and there. It will be very useful tool, just like the block sphere that we study in